Hi everyone, now we continue our lecture on Poisson ratio. So this is continue from chapter A, alright? So when a deformable body is subjected to a force, not only it does it elongates but it also contracts literally. For example, consider the bar in figure below that has an original radius of r and radius and length L, and is subjected to tensile force P. This force elongates the bar by amount of d and its radius contract by amount d. The strain in longitudinal or axial direction and lateral or radial direction become like this. Okay. When we have the length the bar like this, alright, and we have force, let's say force P, alright, P, it will elongate in longitudinal direction and it will contract in lateral direction, right? If I redraw this in two-dimensional, alright, so let's say this is the original bar, right? Original bar, okay, and then we have force P. Let's say we have force P, okay, then it will become longer. It will become longer, right? It will become longer in longitudinal direction and it will be shorter in lateral direction. This one is longer and this one is shorter, alright? So we call that this direction is longitudinal, and this direction is lateral, alright? So it's longer in longitudinal and shorter in lateral, alright? So that is means, alright? So it's longer by delta over 2 and delta over 2, and it's shorter by radius of delta prime, alright? So this one is delta over 2, this one is also delta over 2, and here is delta prime. So the strain, remember the strain is elongation over original length, alright? So elongation is delta over 2 plus delta over 2, you have delta over original length. So let's say this is your original length, which is L, alright? This is strain in longitudinal, and then we have strain in lateral. We have strain in lateral. Sorry, we have strain in lateral, alright? So strain in lateral, you have delta prime over r. R is your original length. So let's say this is your r lah, r, okay? Delta prime over radius, right? Okay, so what is Poisson ratio? Poisson ratio is defined as strain in lateral over strain in longitudinal, alright? And then we have the minus sign. So Poisson ratio of V or nu, we call it as a nu, alright, is dimensionless properties that relates lateral strain and longitudinal strain. So the value is range between 0 and 0.5. So why negative? Because since the longitudinal elongation is positive, will make the lateral contraction in negative, alright? So you have this negative sign, but the final answer should be positive. Let's say here you have negative, let's say 0.1, for lateral is minus over 0.2, but the final answer you should get 0.5 positive. Alright, longitudinal elongation is positive, lateral is negative. So this one is lateral negative. This is example of if you have this one and then it elongates with this one. Alright, so this part is positive and this part is negative, so you should be like this. Right, this is just an example. Right, so basically Poisson ratio is the ratio of the lateral over longitudinal strain. This is strain. Alright, this is strain. Right, remember strain is elongation over original length. Alright, so this is an example of several materials that have several properties. Let's say we look at aluminium. Right, we look at aluminium. They have density of 2.79, modulus of elasticity 73.1. Okay, we have learned this before. Alright, or modulus Young, remember E is equals to stress over strain. Alright, this graph. Alright, this graph. Okay, the slope of this straight line. This is the modulus of elasticity. Alright, and then we have yield stress. Okay, yield stress is the location where the end of the straight line. This is yield stress. You have for tension and compression are different. Alright, and then we have ultimate stress. Ultimate stress is let's say this is the graph. This is at the top. Okay, this is sigma u. This is the ultimate stress. And then we have elongation, and then we have here is Poisson ratio, as we learned just now. For aluminium we have 0.335. Alright, so we have various of materials here. So in examination, if they just mention the type of materials, you need look at this table, so you can refer what is the value here in your calculation. Alright, so example, so bar made of A36 steel as dimension shown in figure below. If the axial force P is 80 kN, determine the change in its length and the change in dimension of its cross section after applying the loads. The material behave elastically. Alright, so this mentioned that a bar made of A36 steel. Okay, A36 steel. So we have here A36 steel, this one A36. Okay, so you use this data later if you need it in your calculation. Alright, okay, so they're asking you the change in its length and change in the dimension. Okay, change in its length, that means they need you to find that what is delta L and what is delta D lah. Alright, if this is D and this is also H, delta H. Alright, okay, so the normal stress in bar, we have sigma is equals to force over A. Alright, remember, so we have 80 kilonewton over A area, which is 0.1 here times 50. Alright, so you got the value 16.0 times 6 Pascal or 16 mega Pascal. Alright, so from table 1 for A36 steel, E is modulus of elasticity or modulus Young is 200 gigapascal. and so the strain in the z direction is, so you use this equation. Alright, remember from our previous lecture, sigma over strain is equals to E. Alright, so sigma over E is also equals to strain. Alright, so sigma is 16 from here over E. E from table, you get 80 times 10 to the power of minus 6 mm over mm. So you have this one, strain in z direction. Okay, strain in z direction. So this is that z direction. Alright, so strain in this direction is sigma over E. You get this one. Alright, so elongation in axial. Alright, elongation in axial, you use the strain equation. So strain equation is delta L over L naught. Pemanjangan elongation over original length. Or you have delta L over strain over L naught. Okay, same with this one. Alright, same with this one. This one also delta L is over strain over L naught. Alright, so strain you have 80 here. Alright, times original length. Original length is 1.5. So original length is 1.5. Alright, so elongation is 120 mu m. So mu m is basically 10 to the power of minus 6. Alright, so from table as well, we have Poisson ratio is 0.32. Alright, so the contraction strain in both x and y direction are, you have sigma epsilon is equals to V over ET. Alright, so when we have this figure, okay, or we have this parts. Alright, so in z direction is longitudinal. Alright, so the z direction is basically longitudinal. Alright, and s direction is lateral, and y direction is also lateral. Alright, so we have z direction, just z direction is longitudinal, so other direction is lateral. Alright, so remember the Poisson ratio formula is E lateral over epsilon longitudinal. Alright, and we have minus sign. Alright, so same with here. Alright, so we have V is equals to E lateral or EX over EZ. Also we have V or nu EY over EZ is same. Both epsilon X and epsilon Y both are lateral. Alright, so we have same equation. Alright, here EX and EY is equals to V times nu times epsilon Z. Alright, so we have 0.32 from here times epsilon Z. Epsilon Z is from here. Alright, so you have minus 25.6 mu m over m. Alright, so this is your answer for epsilon. Alright, so those the change in the dimension are delta x is equals to epsilon x times Lx. So this is equation of the strain, like this equation. Alright, still be using this equation. This one is delta L, and this one is epsilon, and this one is L naught. Alright, apply for each direction. In x direction, we have minus 25.6, this one, and then times 0.1, which is length in x direction, Lx. So Lx is 0.1. Alright, so you have here. Okay, and then we have delta y. Delta y is also same. We have minus 25.6 times 10 to the power of minus 6, alright, times 0.05 meter, because the y direction in 50 mm, so you have 0.05 meter. You got minus 1.28 mu m. Alright, so this one is basically same with this one, so don't confuse with this units. Also they have 25.6 times 10 minus 6 m over m, same thing. Alright, because the units for strain is meter over meter or mm over mm, it's same. Alright, so so you get the answer. Okay, so the change in dimension for delta x are minus 2.5 micrometer, and delta y is minus 1.28 micrometer. So in x and y direction, it will shorten by this value. Alright, but in z direction, it will longer. This is longer for this value. Right, if I draw this in 2D, alright, this is original length, and then this is your elongation. Alright, so this will elongates around 1 to 0, and this one will be shorter around 2.56 micrometer. Let's say this is your x direction and this is your z direction. Okay, so we go to the next example. We have the, let's say, elastic portion of stress strain diagram for a steel alloy, as shown in figure. The specimen from which it was obtained had an original diameter of 13 mm and gauge length of 50 mm. When the load applied to the specimen is 50 km, the diameter is 12.99265 mm. So determine the Poisson ratio of the material. Alright, we have a specimen. Right, we have a specimen like this. Okay, this is the standard shape of the specimen. Alright, the gauge length, okay, is measured somewhere here. It's 50 mm, and then the diameter here is 13 mm. Alright, and then the load is 50 kilonewton is applied. So we have a little bit longer. Alright, and the load is applied here 50 kilonewton, here also 50 kilonewton. Suddenly this become 12.99265 mm. Okay, so the length is not given lah, how much. Okay, it is L final. Alright, so find the Poisson ratio for the materials. Is given also this figure. What we can obtain from this figure, one is of course we have E. Okay, E is the slope for this one. For slope is basically 400 divided by 0.002 is equals to 200 gigapascal. This one is megapascal, right? So actually it's given already in here. Alright, so you got this value also, 200 gigapascal. Alright, so they're asking for the Poisson ratio. Okay, remember Poisson ratio is E lateral over epsilon longitudinal. Alright, minus sign. Okay, so which one is lateral? Okay, so this side is longitudinal. Okay, so this direction is lateral. Alright, the one with the force, so you have force in this direction, so this direction is longitudinal. Okay, alright, so the direction which no force is lateral. Alright, so you need to find what is epsilon lateral and what is epsilon longitudinal. Okay, so epsilon lateral, what is change in diameter? Alright, what is change in diameter is basically here. Okay, D final, which is 12.99265 minus 13 original diameter over original diameter. So you get this value. Okay, minus 0.5658 times 10 to the power of minus 3 mm over mm. And then find what is E longitudinal. Alright, so same thing, delta L over L. So pemanjangan, you can use this equation. Okay, but you don't know what is the elongation of the things, right? So you can find the elongation of that things. Delta L over 15, 0.0, I think it's 50 mm. So 50 mm is around 0.05, 1, 2, 3. Alright, and then this is L final over L initial. L initial is 0.05 over 0.05. Alright, so L final, you can find it using, can we find the L final? Okay, if you cannot find the L final, you can find using this equation. Alright, you can use using this equation, which is remember E is sigma over epsilon. Alright, so E we get here is 200 gigapascal. Sigma is basically P over A. Alright, P is 50 kilonewton, A is the area. You got 367. Alright, 376. Alright, and then you get the elongation here. Okay, you get the elongation. So elongation are basically here 1.88335. So you get directly 1.8835. Okay, so this is a bit tricky. You cannot use this equation, but you can use other equation that contain the epsilon. Alright, which is E sigma over epsilon. So you get both E longitudinal and both E lateral, and you can find what is Poisson ratio. Alright, or from here you get the what is sigma, right? 367. So sigma 367 is around here. Here is 367, and then you can find what is the value of epsilon here. Okay, this is by estimation, and then this is epsilon longitudinal. This value should be 0.0018 lah. Alright, from this value. Alright, 18835. Also same. Okay. So next we go into the shear stress strain diagram. Okay. So before we learn regarding the normal shear stress diagram, we also have the shear stress diagram. So the difference is that here instead we using sigma, here we using tau. Okay, instead we using epsilon, here we using gamma. Alright, this is for shear. So the equation are same. The slope for this value basically before we use E modulus Young, but here we use the shear modulus of elasticity or the modulus of rigidity, G. Alright. Okay, it's similar with E is equals to sigma is equals to E epsilon. Okay, it's similar. Okay, it's similar. Alright, so here we have another thing. This is for normal, this is for shear. Alright, so for relation between Poisson ratio and G are related by this equation. Alright, so you just remember lah. So relation between modulus Young, Poisson ratio and G. Okay, this equation. Alright, remember G is same with E. Instead G is for shear, E is for normal. This is strength parameter. Okay, if we refer to the table, alright, so G is here. Alright, this is for shear, modulus of rigidity, and this is for normal or modulus of elasticity. Alright, it's given here, the value of G, modulus of rigidity. Alright, it's slope for this graph. Okay, it's slope for this graph. If I can repeat, if you have sigma, you have epsilon, the slope for this one is E. Okay, if you have tau and you have gamma, the slope for this one is G. Alright, same thing. Okay. Example, an aluminium specimen shown in figure has diameter of D naught 25 mm and gauge length 250. If force 165 elongates the gauge length 1.2 mm, so find the modulus of elasticity. This one is E. Also determined by how much the force causes the diameter of specimen to contract. Take G is 26 gigapascal and sigma yield is 440. Where is sigma yield? If we draw sigma over strain diagram and we have graph like this, alright, so sigma yield is around at the end of the straight line here, and this one is your E, modulus of elasticity. Alright, modulus of elasticity, the average normal stress. So sigma is force over A, 165 over area. Alright, area you got 336, and the strain are elongation over original length. So elongation is 1.2 here over original length must be same dimension. 250, you get this value. Alright, so you get the value 336 is below than 440, so this is elastic. Is over than 440 is plastic. Alright, so that means the value here is in this region. Alright, in this region. Okay, so the modulus of elasticity is sigma over strain. So 336 over 0048. So here is 336 and here is 0.0480. Okay, so the slope is here 70 gigapascal. Alright, next question number 1. So determine by how much the force cause the diameter of specimens to contract. So when we pull this, it become longer, but the diameter will shrink. Okay, it become shorter here. It become shorter. So they need to know how much it's shorter. So first we determine the Poisson ratio for the material. So you have G, we have E, so you find V using equation. G is given 26 gigapascal. Alright, so E is 70 gigapascal, we get from previous works. Alright, and we had the value of Poisson ratio, which is 0.346. Okay, so since epsilon longitudinal 0.0048, so we get here 0.48. Why longitudinal? Because it elongates in this direction, the same direction with force. So this is elongation, this is longitudinal. Alright, so epsilon longitudinal is below. Remember the formula for the Poisson ratio is epsilon lateral over epsilon longitudinal. So V we have 346 times with 0.0048, you get the epsilon lateral, which is 0.00166 mm. Alright, so the contraction of diameter is basically delta D or delta L over, epsilon is delta L over L naught. Also same, delta D over D naught. Alright, so here we get the 0.00166 equals to delta D over D naught is 25 mm. Alright, so you times these two, so you get the value 0.0415. So if this is n in mm, this one should be also in mm. Alright, okay, we go to the next example. So the shear stress diagram for steel alloy is shown in figure. If in a boat having a diameter of 5 mm, determine the modulus of elasticity and force B required to cause the material to yield. Okay, so what is required material to yield? Take V is 0.3. So this one we have stress strain diagram. Alright, so you have tau, you have gamma, so you should got the value of G. Okay, G is tau over gamma. Alright, which is 350 over 0.05, which is the slope for this one. Okay, so you have 350 over 0.04, you get this value 87.5 10 to the power of 3 megapascal. So the relation, you have G, you have V, so you can find E. E is 227.5 10 to the power of 3 megapascal. So this is your modulus of elasticity, because the question is asking for the modulus of elasticity. So remember this equation. Alright, So yield stress, the bolt is subjected to yielding stress of Vy P. From the strain stress diagram, tau y is 350. Okay, this is the simple equation. You have same with before. Remember, sigma is P over A, tau is V over A. Okay, just use this equation. You have tau 350 force over the area, so you get this. What is your force? If this double shear, you just use this equation 2a. So this is for single shear. Look at this bolt. So this is your single shear. Alright. Okay, I think that's all.